Foundation Models for Embodied Decision-Making Agents, Part 18. This is a presentation by Marco Pavone, Stanford. He gave a presentation at UPenn, and this really is the heart of what we've been working on in the last couple of months, and I think, in our opinion, the heart of robotics going forward. It is how can we use foundation models to benefit robotics? How can we use foundation models to take advantage of them or improve robotics or even breakthrough in robotics? I mean, these are all open questions. Marco says in the talk, like, I actually have to convince myself of what's possible here because the possibilities are huge. There's really four areas that he's focusing on. One is simulation, then semantics, architecture, and out-of-order distribution. I'm going to talk about all of these in detail. But fundamentally, I think what this talk really is trying to get across is that there's a new kid on the block. It's called Foundation Model, and it enables, amongst other things, Gen AI. And that is something we have to take seriously as roboticists because of the reasons I just said: simulation, semantics, architecture, and OOD. So let's start. Let's start with simulation. So Marco goes through the presentation and really shows potential of what can be done, some of his work. They're going to have a paper at CVPR that I'm very curious about. So in terms of simulation, what's possible is what you can capture images, and then you can use Gen AI to create more trajectories based on that image. So you can have a traffic crossing, and you can have all kinds of different scenarios that traffic crossing entails, and then you could have a robot in simulation learning how to drive. So this is, I think, the holy grail of simulation, and it in particular allows for counterfactuals and for edge cases. The counterfactual would be you just narrowly avoided an accident, but you want to go through all the counterfactuals. Actually, you want to use, let's say, if you use Q-learning, you want the agent to have seen a scenario where there was an accident, so it got a negative reward, and therefore that's a stronger incentive not to do whatever it did to lead to the accident. You can't have counterfactuals in online reinforcement learning, but you can have it in simulation, and then in simulation you can be online or offline. You can be model based or model free. That's not so key. I think again, in simulation, I think we have mainly the Gen AI part. I think is the interesting part, but you can even go to the actual vision part, and you can then introduce the inverse graphics problem, of which he hasn't been talking about too much. But the inverse graphic problem is sort of capturing some of the physics in the picture and have it then used in sim. So can we basically, fundamentally, the idea is can we use 3D images? Can we picture a 3D scene, so a real scene, in the 2D, and then transfer that 2D into a 3D representation in terms of physics, and then learn on that? That's really the big question. The other thing he's talking about is semantics. Now, semantics, again, it can be used in training, and it can be used online. So what that means in training, we can actually train a model with additional semantics. So we could have the car being, while the foundation model is being trained. So while the training of the model entails semantics such as you should never drive around, driving around children is more risky than driving around adults, or like those types of semantics could be embodied in the training or embedded in the training. But you could definitely use it online then. and that's what I've been talking about for a while now that I'm a user of FSD, that we need semantic maps. We need more intelligence around the maps that we have. Maps 1.0 was about location. Maps 2.0 is about semantics. It's not enough just to get to the school and pick up your child. You need to understand what's going on in the driveway. I think that's what a robot needs to understand. If you watch FSD in New York City, for example, going through Midtown New York City, there is one way to learn about these types of environments actually would be to add semantics to the equation. So the reason we have semantics in foundation models is because we have access to a deep knowledge base that we gathered at internet scale. So we input knowledge to the internet that is compressed in a foundation model, let's say a large language model like GPT, and we can use that knowledge. We can augment the knowledge of a model with those types of semantics. That's something Google Maps doesn't have. This brings me to the third thing, the architecture. He talks about the architecture, and you know, these things are all intertwined, of course, because what does it mean, architecture? So let's say we want to train a model end to end. First, just from an engineering perspective, the way autonomous vehicles were trained in the past was modular. So there was a module for detection, for perception, there was a module for mapping, there was a module for planning, there was a module for out of order detection, for example. And with some new techniques, we can actually have all of these modules interconnected and differentiable, and therefore we can have end-to-end training. The upside is that we have one big function approximator, so we're not optimizing for perception and then optimizing for planning and optimizing for mapping. It's one big network. If we use the AlphaGo zero analogy, it would be, imagine if you had a model that is just training how to detect where the pieces are, another model trains what should be done, and a third model maybe trains something else. That would be weird. Like we want to have a one end-to-end training, and that's possible with the fully differentiable architectures. But what Marco is emphasizing here is that the design space is pretty big in terms of, okay, how do we actually put all these pieces together? And what he's suggesting is sort of a modular approach towards modularity. Excuse me for that. It's a mouthful. But what that means is we could probably experiment a little bit about how we connect all these different parts of the training module. And one of the solutions he comes up with, and there's a paper in CVPR that will talk about this, it's sort of think of a foundation model as a backbone. So you have a large internet scale pre-trained foundation model. It could be just trained on text, or it could be trained on text and video, and let's just leave it at text and video. And that's sort of a backbone, and then you add specific fine-tuned models such as perception, mapping on top of that. So you kind of use the backbone for semantics or other for semantics in particular, but also you can be much faster. Let's say you have a traffic scenario where maybe you need a lot of data to learn how to act in that traffic scenario, or you could just use a large language model which could give you the semantics and say, I think the best is you just take the left lane and turn left, and you don't bother with the construction in the middle. Like you could have a faster shortcut towards the solution by using semantics. So we're circling back to semantics. I think semantics is really the big one here. It's a big theme that goes through, I think, all the work that people are doing in robotics right now with the conjunction of foundation models. And I think that is the big opportunity. Another thing that is really close to Marco Pavone's backyard, if you will, is out-of-order detection. Actually, Somrita, one of his PhD students or PhD students within his lab, she presented yesterday at the robotics seminar, and I already have an episode out where she spoke about out-of-order detection. Now, out-of-order detection is a big, I think it, like I have a fully dedicated episode, just check out May 3rd. I want to mention here that I think it's out-of-order detection is really philosophically a very deep topic, because you can say that if you have a lot of out-of-order distribution, meaning if a lot of data comes in while you're online, while you're driving, let's say an autonomous vehicle, if a lot of data comes in that the vehicle doesn't know what to do with, then that means it's just not trained well, right? So any kind of out-of-order distribution event could also just mean, well, that the model wasn't trained well enough. And I think foundation models, the goal of foundation models, by the way, the definition of foundation models, trained on wide range of data in self-supervised way and can be adapted to various downstream tasks. This is what the foundation model definition is, according to the Center for Foundation Model Research at Stanford. So again, trained on a wide range of data in a self-supervised way and can be adapted to various downstream tasks. I think fundamentally what it is, it's very general. Okay, it's wide data, self-supervised. There's no heuristics here. We're not labeling anything. We're not interfering. There's as little as possible human heuristics in here. Now we're using that as a backbone to then, for example, do out-of-order detection. So if I see a red light which is mounted on a truck, and that red light's driving on the highway, and the car sees a red light in the middle of the highway, the car can, through a simple prompt on a large language model or a vision language model, he can see, okay, this is a red light mounted on a truck, and then the conclusion would be you can just keep driving because it's not a real red light. Other scenarios in self-driving, you have a stop sign in front of a billboard. So is this now a stop sign, or is this a stop sign on a billboard? Things along those lines can be detected. So again, out of distribution really means, it just means that you haven't seen that data. And if you have a foundation model, the goal of the foundation model, and we discussed this yesterday at length, I'm just repeating, what is a foundation model really? What is GPT? GPT takes text from the internet and in parallel trains all kinds of relationships between the tokens and embeds that in a latent space. So then that knowledge, compressed knowledge, can be accessed by a machine. This embedding can be used also for multimodal representation of the real world. And we could therefore find out, let's say that, in this particular case, the red light really was mounted on a truck, and that is not something that the model should be worried about. We can also use that out-of-order detection as one thing, as a warning. So, okay, you got to be careful, but also as a step forward learning. So you can say, this is out of order, now let's put that in the training set so we can learn. So there's kind of a continuous learning process. So to summarize, Marco Pavone's presentation is really dear to our heart. It's what we think autonomous driving will look like in the future by embedding, incorporating foundation models, the ideal foundation models. So there's two aspects here. One is fundamentally the idea. So we can just start from scratch and train models based on the foundation model architecture. But then second, we can also use some of the foundation models that are available, in particular the text-based, like GPT and Claude, and then visual language models and other types of multimodal models. Maybe there are some third way type trainings where we can have maybe a mode independent, a sensor independent data set where we just bring in text and video and sound and put that in a sort of embedding that then clusters in an unsupervised way what belongs together and does self-attention and cross-attention. and then potentially finds out things that we humans don't even pay attention to. I mean, this is, of course, the holy grail of all of this is, can we build machines that can do better than humans? Not necessarily better in terms of better drivers or any of that, but at least they can do better in terms of avoiding accidents, because they have more access. They have access to a deeper representation of the world than we have, because again they have more sensors, different types of sensors. And fundamentally, what Mark was saying is that we can have 4 concrete applications of foundation models in robotics. One is in simulation. We can use foundation models and Gen AI to create better simulation machines. In particular, we can have a better representation of the real world in sim, and then we can have more trajectories and use Q-learning with the additional trajectories to learn more edge cases, and therefore have less out of distribution data, because we've trained on much more potential scenarios. Semantics, we can add semantics, which is the difference between a semantic map and a Google map, is that the semantic map has a sense for that, playing children on the side is not the same thing like adults standing on the side, or the canonical issue with the man waving or the man saying halt. From a occupancy network perspective, this could be the same interpretation, but with semantics it's very different. And then architecture-wise, it's really the holy grail here is, of course, end-to-end training, which we can have now because we have fully differentiable techniques for modular architectures. But there's still a lot of work to be done in experimenting of how to put the modules, let's say, in the case of autonomous vehicles, the map, the object detection, the dynamics, the planning. All of these things can have different type of specified training modules, but then they can be put together maybe by being attached to a fundamental foundation model backbone, and then through the fully differentiable aspect of it, we can use forward and backward propagation and train the model truly end-to-end, which is, just to end the episode, we don't know exactly what Tesla is doing, but that's what they claim they're doing. I think academia is a little bit behind the industry here, because academia has to come up with ideas and then write papers and do some math and experiments, versus businesses, they just try and error, and then when they ship products, that's something concrete. It's like publishing a paper, but it's sometimes not as rigorous. In some ways it's more rigorous, and in some ways it's not. But we believe that industry is moving faster. Marco also says that there's less legacy attached to industry, because there's always going to be newcomers that are not married to some old-fashioned way of doing things. But I think fundamentally, just to finish this episode, I think the opportunity with foundation models in robotics comes from a condensed knowledge representation that is available in text. It comes from the ability to train in a new way, in a multimodal way, and therefore maybe circumvent some of the labeling and scaling hindrances that were there before. I think we can experiment with the architectures, and we can have semantics added to the mapping in particular that can really enhance the experience of a autonomous vehicle. Thank you.